Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Continuing our trig stuff as you step on inside this virtual classroom, we have graphed sine and cosine graphs together. We've talked about the change in amplitude, horizontal shifts, vertical shifts, frequency with period, etc., and then doing them with tangent functions, which looks a little different. I'm going to enrich on all of that stuff here. This one won't focus on tangent as much. I think there's one little talk on tangent here, but mostly I'm going to go back to the sine and cosine graphs, and just in general what I'm going to change with some of these things. I do want to graph a couple negatives or show you what the negative graphs look like on a couple of these. I want to talk about what happens when the frequency includes pi and the scaling of the graph do not, and then I also want to write equations off of graphs and then do a couple word problems, and those word problems will both be the same kind of premise. They'll only be sine and cosine based, but off the same premise of, I think it's a Ferris wheel. And then there are other kinds we can do. I'm sure when I review, I'll cover different kinds there. But I'll jump straight into it. I believe it's only 8 problems in total. They could have some good new conversation going on. I will have you know that if you have not seen my previous videos on how to graph sine and cosine functions in general, you may be a little lost or this may be a little fast. This intent is on enriching that stuff with the new stuff. So I hope that makes sense. Okay, the first two are the only two you're going to graph besides before the word problems. The only two you're going to graph based on the equations. So right here, we have y equals -4 times sine of x minus pi. Now, if you watch my previous videos, then you would have known how to graph it if it was just a positive 4 right there, which is fine. Everything's going to be the same on this except for how we initiate from our starting point going down instead of up. And that's the good news. So with a k value of 0 with no vertical shift, our midline will be at y equals 0, the x-axis. We will start on the midline because it's a sine function. However, we don't start on x equals 0. We'll start on x equals pi because of the minus pi over there, which would give you the sine of 0. So the amplitude being 4, meaning you'll go up 4 units from midline to peak and down 4 units from midline to trough there. We will be doing that still every pi over 2 radians to hit another critical point, peak, peak, midline, trough, midline, etc. But instead of starting to go up, as sine of pi over 2 would be 1, or times 4 is 4, sine of pi over 2 is 1 times -4 is -4. We'll be going down 4 instead of up 4. So we're going to start by hitting trough and then peak and then midline, as opposed to peak and then midline. Now I would hit peak next, but I can't fit it. So basically the whole cycle would have done this instead of this. So it's reflected over the x-axis. Since I can't fit those points in this window, I will continue backwards and get these other points there and get the graph. So again, if this is your first time with me on this graph stuff, you probably want to go back to some of the previous ones. It might take you some time, but that's the point. It does take time. And this, like I said, is the enriched material from that. So there is a sine graph there. Probably not the best curves here that you'll have seen, at least from me. I could do better than that. I should aim to do better than that. No matter, we're good. Please draw those arrows. This thing does continue infinitely on that domain. And the range just goes from -4 to 4. It should never eclipse those. All right, number 2, y equals cosine of pi over 2x plus 1. Now, if you've been with me before, you would be fine with 1/2 x perhaps. And actually, at the time, you would have seen it say theta over 2, something I'm not a fan of in 2 ways. 1 being a theta and 2 being dividing it by 2 rather than seeing it in front as what the actual value is for itself. And I much prefer this right there. But the other thing is there's a pi involved now. Now what we did learn was that the period of a sine or cosine graph by default is 2 pi. If you divide it by the frequency b, this is b by the way, if you divide it by the frequency b, then you will get the period for your current function that you're looking at. So what I'm going to do is determine the period of this function by dividing 2 pi by the b value, which is pi over 2. Now, as we know, dividing by a fraction is the same thing as multiplying by the denominator's reciprocal, so 2 over pi times 2 over pi. The pi over pi becomes 1, they're gone, and 2 times 2 is 4. Your period is 4, not 4 pi, but 4. That means it takes 4 units on x to complete an entire cycle of your period. I mean, 4 is your period. 4 is your wavelength. That's how long it's going to take. So that entire period of 4 is completed on a cosine graph. It doesn't start here. I'm just saying completed on 4 from point to point. It should take 4 units in total. So we'll go ahead and do that. So this is a +1 midline right here. Our cosine graph starts a units above or below the midline at your h value. The h value seems to be 0, no horizontal shift. So instead of starting right here at the midline, we will be a units 1 unit above the midline right there. That is our peak. And this 4 represents how long it's going to take to get back to this peak again. So 1, 2, 3, 4 over will hit the peak. And you might notice here that these are actually just integers. They are not pi over this or 2, or just 1 pi, 2 pi, 3 pi, 4 pi. They don't have pi in it because pi is represented in the frequency, not the period. So you can see that little change, and you will see this in the word problems, because the word problems, we generally count things using integers, specifically with time. Excuse me, a little scratchy nose. So what I do need to find out are the points in between. They're not going to be too hard here, because when you divide 4 by 4, you get 1, and 1 represents a quarter of your period, and a quarter of your period represents another critical point of a midline, peak, or trough. So we start at a peak, we'll go down to midline, down to trough, which is the bottom, up to midline, and back up to peak, and that is an entire period on cosine. And then you would repeat the process for whatever you can fit, which is what I'm about to do right here. So this is how the pi over 2 version works. It's not hard at all. In fact, it's rather helpful when it comes to your graph, because you have less in the way of having pi's in your scale, especially because pi tends to also lend to having the fraction versions, pi over 2 and pi over 4 and stuff like that. That's not necessarily true. You could have fractions with your integers, but one less symbol, I think, is good for most students to see. All right, that's number 2. All right, numbers 3 through 6 right here. We have 4 different graphs. Only one of them is a tangent. The other are either sine or cosine. And, you know, I have to plot these because they're not on here. I had to put them in after I printed them. So let me do this right now. I hope I remember these correctly. I think it was here, here, I think so, here, and you might not see this one, but I'll get to it later, and here. I provided a reference point for my students for each of these so that we could consistently have the same equation and they could practice certain things so they're not always stuck on just sine or cosine when they're doing these things here. It says write equations for the following trig functions, use reference points shown. So now the reference point that I provided is the one I want you to use. And, you know, it does make a difference. There is an infinite number of equations, and I'm not joking, literally. There is an infinite number of equations that you could write to represent this single graph, because as the arrows indicated from before, these graphs go forever. So you can change this from a sine graph like this one will be to a cosine graph like this would have been right here. Or you can change where your h is, where your starting point is on sine, and make it a positive sine graph or a negative sine graph and whatever. You can go all the way across your infinite domain. It's literally an infinite number of equations you could put. There's no wrong answer. There's no limited number of correct answers. And so I'm limiting it to just one. So that's what we're going to do. We're going to choose this point as if this were the starting point. If someone took your equation and wanted to use this as a starting point, what would this equation look like? So we're going to do that. So what are some consistencies regardless of where the starting point is? One is the midline, and seeing that your peak is at 3 and your trough is at 1, the average of those values is 2, right in the middle. That is your midline, of course. Let me put it behind if I can. Nope. Hold on. I want that. There we go. That is your midline there. Now, the amplitude is the distance between peak and midline. So here's what we want to do. Our form comes in the form of y equals a times sine of b times x minus h plus k. By default, without any transformations, a would be 1, b would be 1, h would be 0, k would be 0. 0, 0. We're trying to see how these are potentially affected, and if they are not affected from those, then they might not be visually included, but we still have to determine them. A represents the midline. We want to find out what your A is. The midline is the distance between peak and trough. Sorry, your amplitude, I probably said all of that wrong. A represents your amplitude. Your amplitude is the distance from the midline to the peak and the midline to the trough. That A value is 1. Now, if it's a sine graph, I'm talking about this all out of order. I'm very sorry. My mind was on something else for a moment. let me kind of talk about that again. This is going to be a sine graph. It was either sine or cosine because of the midline itself being represented right in the middle there. We start on the midline as a reference point, and sine graphs do that. Cosine graphs do not. They start at peak or trough. And let me actually mention midline as well. The midline value is 2. That's kind of where we'd start with anyway. Based on the midline there, we can determine the distance from the midline to the peak and midline to the trough is just 1. And because this sine graph starts by going up, then the stretch factor is a positive 1. It's not a reflection there. I'll actually save B for last here. H is also a part of that starting point. And honestly, if I were to go about this in order, I probably should have started with K and H. And then next time I'll do A and then B. So the H value is the horizontal shift from x equals 0 right here. And we shifted to the right a certain number of units, which is halfway between 0 and pi over 2 right there. And that value happens to be pi over 4. Just like a quarter is halfway of the distance between 0 and 1/2. That's kind of something you'd have to know, or you can, of course, calculate taking half of it. I think you'll have to kind of assume that's halfway in between, and when you look at all the other points that are in line with it, that seems to be the case. So your h value here is pi over 4. Now, in your equation, when you see this minus h, we'll make it a minus pi over 4. That's fine, but just understanding that's there. Okay, and then next is the b value, which is frequency. Frequency is determined based on period. And we happen to know the equation that period is 2 pi over b for sine and cosine graphs. Well, if you rework this calculation stuff, you will actually also get that you can find b by doing 2 pi over p right here. So you can get b by itself by dividing 2 pi by the period, and we can use the graph to determine what the period of this function is by saying how far do we go from one point to another in terms of coterminality. And some people have trouble with these things, especially when it comes to fractions and pi's and gaps in between and things like that. But this value here is at pi over 4, for example, right here. That's at pi over 4. Where's another point that's coterminal with it? I can't find one to the right, but here's one to the left right here. What's that distance from this one to this one? This goes from pi over 4 to negative 7 pi over 4 right there. You can do a subtraction to figure that one out. You would get 8 pi over 4. That's 1, 2, 3, 4, 5, 6, 7, 8 pi over 4, which is 2 pi. You could, of course, also line this up. Sorry that this is going to go along with it. You can line this up wherever you wanted. The point is this is supposed to be a 2 pi distance, even though I didn't really seem to scale that very well. But this is supposed to be a 2 pi distance between those guys right there. And that is your period. So the period is 2 pi. So the b value will be 2 pi over the p, which is 2 pi, which is 1. So your b value is 1. That's a normal frequency because this is a normal period on your sine graph, even though it's shifted up and over. So what is the equation now? This would be y equals, if your a value is 1, I probably just won't write it. So sine of, if the b value is 1, I probably just won't write it. So I'll write x minus pi over 4. And then your k value is 2, so plus 2. So that's how you can kind of do the equation based on that right there. I think that's a good way to do it, and I should probably make sure to do that next time. I'd kind of do it the same way I'd graph. I would start with the midline, kind of find the starting point from there. Also determine what kind of function it is, of course, and then go from there. Okay, so next one, the second one right here in the same vein. Is it a sine or cosine graph? Well, let's start with the midline. That'd go right on the x-axis here, right in the middle. That kind of lends to what the k value is. It looks like the k is 0 in that regard. But is this a sine or cosine graph this time? Well, this time because your starting point, reference-wise, is not on the midline, but a peak or trough, it appears to be a cosine graph this time. So instead of sine, we talk in cosine. Now the h value also appears to be 0, given that there is no horizontal translation on this thing from the starting point. This is all about how a and b may potentially change. So let's look at those exactly here. Now a is the distance from midline to peak or trough. It's that amplitude. The amplitude by default is generally 1, how far up we'd go here. Now it looks like we're only going half that distance instead. We're going up halfway or down halfway. So the a, well, the amplitude is 1/2. But because it's a cosine graph, normally, cosine of 0 is 1. So normally we'd start a unit or half a unit above the midline, but now we're starting below the midline. What does that mean? It means this graph is reflected across the x-axis in some sort of way. It is flipped to the point that you have a negative stretch factor right there. A is negative 1/2 because of that. The b value, on the other hand, needs to have us compute the distance from one point to another coterminal point, such as the distance from our reference point here all the way to this other trough right there. The distance from 0 to pi, well, is pi. So your b value being 2 pi over p, 2 pi over p here, the b value now here would be 2 pi over pi, which is 2. The b value is 2. Your frequency is 2. So the equation, as I can remember how this thing works here, remember it's a cosine graph, is going to be y equals negative 1/2 times the cosine of, well, I don't need a square bracket because there's no h or k for that matter, but cosine of 2x. And you technically don't need square brackets anyway, but I would need another set of parentheses if I leave the b value factored out of a quantity, some x minus h. Something like that. Give me one moment as you're maybe writing that out. Now, a student asked me, why is it important to find b when it's not on the graph? And listen, you can argue that it is on the graph because it takes twice as many. The default period for a cosine graph would have been 2 pi. So basically, it would have taken this amount of time to complete a full, I don't know, cycle. I'm not doing this right, but you know, there are two of these covered over the span of what would have instead just been one time to take. I think so from here to here instead it would have been, right? But it doesn't matter how 2 is used in the graph. The question is, what's the equation for the graph? So you don't use 2 for the graph, you use the period on the graph, and we use the graph to find the period and the period to find the frequency. We're coming up with the equation that makes the graph, not the graph that makes from the equation. Okay, early morning. Number 5. We have another sine or cosine graph. This is the midline right in the middle here. I think you could agree this would be a sine graph here because starting on the midline. And it appears to be another positive sine graph as well, but this time we seem to have some new changes in mind, especially on the x-axis here. As you can see, we have integers, not pi values. So how does that work? Well, let's determine a, b, h, and k. So let's start with k. It is 0 again because of that midline being on the x-axis right there. Your h seems to be shifted 1 unit over. That does mean an h value of 1, indeed. The b value here, the frequency, is definitely something that changed somehow. What is the distance from one point, any one point, to its coterminal point, such as this guy over here? We're going from 1 to 5. From 1 to 5 right there, that distance is 4. That makes your period 4. So the b is 2 pi over your period of 4, which is pi over 2. That is the value that goes into your equation bit. And a is the distance between midline and peak, midline and trough. That is 3. And because we start, this is a sine graph, by the way, because we're starting with that sine there and going upward from that to the positive, to the peak, it is going to be a positive 3 as well. So there's your information, and we can now write the equation as y equals 3 times the sine of, and this is where I have to kind of put the square bracket, so I'm going to put pi over 2 here, factored out of x minus 1, like that. And there is our equation. And lastly, number 6, that is full-on tangent. Let me move myself over. Full-on tangent graph right here on number 6. Let's start with that midline right here, definitely going across right there like that. And given that it's tangent, tangent graphs, first of all, their default period is actually pi, not 2 pi. It actually only takes pi units for it to repeat exactly what it does. So we're going to determine period based on pi, b, frequency based on pi over p, or pi over p, not 2 pi over p. Secondly, tangent graphs actually tend to go this way instead. So when you have something starting on a midline, which is what we'd expect when it comes to reference points there, it would tend to go up, but since it's going down, we also know that we are going to be dealing with a negative a value there. Okay, so let's start by talking about that midline though. So a, b, h, k, give me a moment. The midline there, I don't know if that's what you call it, but it's a vertical shift. We're going down 1 unit, so that's a negative 1. And when you look at the h value as far as where this starts, it does start at pi over 6. So we are good on those two fronts so far. Now, the a value, the one thing that's kind of missing in this tangent graph, where we would generally have the in-betweens, and I know it's kind of hard to see how they come to play, but there's like a pi over 12 right here, and like a pi over 4 that's right there. But these points should exist. Let me kind of plot them. These points should kind of exist here. These are the ones that we generally like to use to consider, because there's no peak and trough, but at those tangent of pi over 4 kinds of values where we should get 1 and -1 like that, that's what these ones are here. And we are still going up and down 1 from the midline. That makes your a value, that stretch, be a 1. But because it is negative, the a value will be a -1 instead. So, this amount here, the distance that's halfway between your midline points in your vertical asymptotes is that one where we should be going 1 up or 1 down. If it was stretched to 2 down, then it would be a -2. And if it was stretched to a half up, it would be a positive 1/2, things like that. But it's a -1. The b value is all that's left. Let's see the distance between any two repeating sets of values. Every set of asymptotes is another repeat of your coterminal stuff before it cycles again. And the distance from 0 to pi over 3 is pi over 3. That's your period. Well, the b value is supposed to be not 2 pi, but pi over your period, pi over 3. So what's pi over pi over 3? Well, it's pi times 3 over pi, which is 3. So the b value is 3. That is your frequency of this thing. It became compressed 3 times smaller. So your equation is going to be y equals -1 times the tangent of, let's do 3 times x minus pi over 6, and then -1. I probably should have somewhere chosen a reference point that was in the negative x value, so we could put a plus there somewhere. That's okay. All right, that's writing equations from those graphs there. Moving on forward, we are just going to do 2 word problems, and they're rather identical. There are some different things that's going to change, but hopefully learning one is just going to make the other make even more sense. Okay, so these word problems are for trig functions that are like sine and cosine. They are like waves that oscillate. Now, that doesn't mean they have to be regarding waves. What this thing is, in fact, and I'm going to jump the gun a little bit. We're going to be measuring height with respect to time right here. So my y-axis is h, and my x-axis is t. So what's happening is, as time goes on, something is going to change in height up and down and up and down. You could consider something regarding degrees in a season, something regarding tides during the time of day, sunrise, sunset kinds of things could have occurred over the course of a season as well. We're going to talk about the height of a position on a Ferris wheel, where although a Ferris wheel goes in circles, the idea of height is the height goes up and down and up and down. Yes, there's left and right position or forward and back, whatever you're thinking of, but that's not being measured here. What you're measuring is the up and downness, the position over time. So as time goes on, at what point are you up and down on it? And it's not jaggedy edge up and down either, because as you go on a Ferris wheel here, you're going upward speed less at the bottom and at the top than you are in the middle. In the middle, you have a higher rate of climb this way, assuming a constant speed, because there's only vertical speed up and down at the middle, whereas over here you're going left, right, or forward, back, or however you want to say it. There's no vertical speed at the bottom, just horizontal, and there's no vertical speed at the top, just horizontal, but there's most speed here. That's why you'll have that fast up climb to slow, and then down climb as time goes on, what's happening there, and that's represented with sine and cosine. And we can use those then to determine certain positions at certain times or certain times for certain positions. All that. So let's do it. A Ferris wheel with radius 40 feet completes 1 revolution every 60 seconds. The lowest point of the wheel is 5 feet above the ground. Draw the graph of the situation, starting with a person getting on at the bottom of the wheel at time 0 seconds. Assume the person gets to ride for 2 revolutions. Okay. A lot of things to unpack where we can come up with a graph based on that information, and we have one kind of pre-scaled to assist you here. And I know I'm kind of in the way here, but down at the end we have 120. You'll see it once we kind of don't need to read the information anymore. Okay, so a Ferris wheel of radius 40 feet. So just so you know, that means that this guy is 40 feet right here. That means that the distance from the middle of the Ferris wheel to the top or to the bottom of the Ferris wheel is 40. That sure sounds like an amplitude to me. So it sounds like A is 40 in that situation. I mean, I think we're going to do the equation first, but that's sure what it sounds like when it comes to the graphs. Now, it says the lowest point of the wheel is 5 feet above the ground, and I think that's the thing that I want to play with most first, is what's the bottom, what's the top, based on having a reference point. We do know that 5 feet above ground would be right here, because that is a quarter of the way up to 20. And if it's a 40-foot radius, that means the middle of the Ferris wheel is right here at 45. And then the top of the Ferris wheel is another 40 away, which is at 85. So a little bit tougher when it comes to scale stuff because they're not right on those numbers, but that's that. That does make this your midline of this thing, as it will hit a peak and trough, high point, low point. Never goes higher than 85 or lower than 80. Now, how do we find all those discernible points? Well, there's an actual starting point that we have based on them saying a person gets on the bottom of the Ferris wheel, the bottom at time 0. So assuming that the Ferris wheel is going or what have you, we can start recording time right at the bottom right here. This is our starting point of sorts, depending on what they want us to make as an equation. It says the Ferris wheel completes one revolution every 60 seconds. That means that if a person started on the bottom, 60 seconds later they would complete this cycle and be back at the bottom. That sounds like something completing a full period right there. So if this time is in seconds right here, something happens in between where he hits the top and back at the bottom 60 seconds later like that. So if that's a full period, if period is 60, then we want to find a quarter of that period. Sorry, period is 60. We take a quarter of the period there to get 15, and that means at every 15-second interval, we are hitting yet another critical point. We are either, here's 15, we're either hitting halfway up at the midline, or we're hitting the very top another 15 seconds later here at this peak, or we hit this midline again, going back down 15 seconds later, and finally at 60 we hit there. And we get to repeat this one more time here, as we get to go another 15 here to 75, another 15 here to 90, another 15 here to 105, and another 15 here to 120, repeating that performance once again, and this ends up representing that curve right here. And as I mentioned before, that's a little too extreme. As I mentioned before, this should be a curve that is, I gotta be a little more precise, this should be a curve like right here that probably should be even better than that there, where you do increase your rate of climb right in the middle, and you decrease it as you come to the top and bottom, just because the nature of verticality around a wheel, especially if the speed is constant around the wheel. Not perfect, but I'll take it. Now, here's the thing about this problem, unlike the previous problems. I am not using arrows here. I'm not using arrows here, and the reason is because this person's domain is from 0 seconds to 120 seconds. That's what they said. They get to ride for 2 revolutions. They don't get to ride for a third. There's nothing after 120 seconds, and they start the ride at 0 seconds in, so there's nothing before that either. So no arrows on this one, but everything in between accounts for where that person's height is at those times. So what we're going to do now is make an equation of this thing, and we're going to use that equation to answer a question afterward. So first, determine a cosine equation representing the path of a person on the Ferris wheel. That specific person right here, I suppose, that if they get on the right at this time here. So they did say a cosine equation, which means we got to pick a reference point that is a trough or at a peak, not a midline, because cosine of 0, we don't start at midline. So I want to start as close to there are kind of one of two things you could choose, but you want to be as close to your y-axis as possible. And sometimes people want to sacrifice the negative version of one for a positive version, but you want to choose the closest one if you can help it. You don't need to choose something farther. So right here, I'm going to choose that 0. That means that given my a, b, h, and k, my h value is actually 0. But a, b, h, and k. So my h value is 0 because there is no horizontal shift, given that this is my starting point. My k value is my midline, which is 45 right here. 45 feet. The a value, I already mentioned this before, this is the amplitude. Your radius is your amplitude, distance from midline to peak and trough, the distance from the center of the Ferris wheel to the top and bottom of it. So it's a value of 40, but because it's a cosine graph that starts below the midline, it'll actually be negative 40. And lastly is the b value. Now we know that the full period of this thing is 60 seconds. So the frequency, for cosine graph, you would take 2 pi and divide by period. So we're going to take 2 pi and divide by 60, and that becomes pi over 30. That's the frequency for this thing. And remember, this is in radians. So your equation here is going to be h of t, I'll say that instead of y, h of t equals negative 40 times the cosine of pi over 30 times x plus 45. Oh, not x, t, excuse me. T plus 45. And you can take that to the bank. You can go and try that with a graphing calculator, see how you do. It should be the same answer right there. And that's what we have. So this models this thing. It should only be modeled from 0 to 120. That's all we can assume the model for. I guess if the Ferris wheel kept going, there's no reason it shouldn't keep repeating its exact cycle. But this is all we're talking about when it comes to domain. I'll just go and say that this t is going from 0 to 120 seconds. All right, determine how high the person will be after writing for 40 seconds. Now, before we actually calculate this thing, understand we will substitute 40 for t. On a graph, you can also get this represented by determining what y value or what h value you get when you go to t on 40 on t. So 40 on t is right here, and if it's drawn well enough, then you'd say that this is about where it would be. This is how high the person would be up. Somewhere around 60, 65, around 65 feet, something like that, getting somewhere around there. I don't know if the graph is drawn perfectly here, but you can kind of estimate, if you had a real graph, you can kind of estimate what that is. That's what we're trying to answer there. And by the way, you're at this height at more than one time. You're just not at multiple heights at the same time. So there's another time which we hit this height, and another time which we hit this height, another time which we hit this height. But we're only asking specifically what the height is at this time. So how do we find out what that exact height is right here? We substitute 40 for t. So I'll go ahead and do h of 40, which is negative 40 times cosine of pi over 30 times t times 40 plus 45. So it's h of 40 equals negative 40 times cosine of, that would be 4 pi over 3. And, you know what's good about that is it's actually a Pythagorean, not Pythagorean triple. It's actually I was thinking of my other class. It's actually a special right triangle. It's a special angle. Cosine of 4 pi over 3 is negative 1/2. So that is negative 40 times negative 1/2 plus 45. Now you can let your calculator do this as well. You'll get obviously the same answer, especially because you're not always on special angles. But even if you didn't know it was a special angle or not, you can let your calculator help you, I suppose. I'm not done. Just make sure your calculator's in radians. Just make sure that it's in radians. Negative 40 times negative 1/2 is positive 20, plus 45 is 65. So there you go. It was 65. And by the way, 65 feet, because we are in context now. So it's supposed to be kind of, yeah, right there, whatever. So 65 feet is the answer, and that's how high they are at 40 seconds in. Okay. Last one, number 8, another Ferris wheel question. Now, I seem to remember, because I saw this before, somehow a 1, it was kind of weird when the problem was generated with this. There was a 1 that was supposed to be here to make this 10 feet, and it didn't translate over, and when I didn't translate it over, I made this graph thing based on the fact that I thought that it was 0. So this was originally supposed to be 10, now it's 0, and because it's 0, it changes the graph and stuff. That's okay, you'd never know one way or the other. But if you're wondering how a Ferris wheel can be 0 feet above the ground, wouldn't people's knees just be scraping the ground and stuff at that point? It could be sunk below ground. There could be an axis point below the ground a little bit. That's okay. All right, a Ferris wheel 120 feet in diameter completes 1 revolution every 180 seconds. The lowest point is 0 feet above ground, so on the ground. Draw the graph of the situation, starting with the person getting at the bottom of the wheel, time t equals 0 seconds. Assume they ride for 4 revolutions. So, what we kind of saw before is, so this time they say diameter of 120 feet, not radius. So this time you're looking at the distance from the trough and the peak when it comes to graph. And when it comes to starting point, they're starting at time 0 at 0 feet instead of 10 feet. Whoopsie. I would change it to a 10. Honestly, I would. But because I can't fit 130 right here, it would probably be about here. but since I don't actually have it, can't really fit it. So I'm just going to go ahead and put it at 0, 0. It's no matter. That's fine. Now, every time a period, 1 revolution is every 180 seconds. So I can go ahead and find myself at 180 right here. Then 4 revolutions total. Another 180 here at 360. Another 180 at 540. And another 180 at 720. So this is completing the revolutions. Now, let's see if we can do this without actually kind of calculating well, sort of. Let's do half of this revolution to get the actual peak, because we know that it's 120 up from 0, which is 120. Half of 180 is 90. So we know that right here we can just keep repeating these by adding 180s, because if every revolution gets, if every 180 seconds gets you to the bottom, then every 180 seconds should also get you to the top. That's the whole idea of coterminality, is that every point gets to do repeats like this. And then same thing with midline. You get to divide that midline by 2 to get 45. Oh, where's that middle? What are these amounts in between? Hold on a second. Half of 90 is 45, right? 30. Half between 30. Yeah, I guess this is 45 right here. Okay. So, oh, by the way, your midline right between 0 and 120 should be 60 right there. So that midline, I guess this is 45 right there. So I'll just hit these 45s as best as I can. There must be 135 and what's next? 225. These should be the if you know your unit circle really well, you should know these as like 315, and then I don't really know them beyond this one here, but just all the 45s that are in between. I'm just eyeballing it from there to get these. But these are ones you do want to get. You do want to hit. Okay. There are your points right there when it comes to graphing. At least we know that portion. And this is the last question, by the way. So, give me a second while I draw this curve here. Yeah, the other kinds of questions that you can run into with these, like I mentioned, because there are a lot of things that have an oscillating pattern. And listen, they're models. They are not perfect. They are projections. Some things are perfect here, but when it comes to projections and stuff, they only assume things as they go, such as, a very popular kind of problem in like physics and calculus questions and stuff is a ball that's thrown up in the air or something like that, and gravity is doing its thing. But you're not accounting for things like air drag, air friction, and stuff like that, and that stuff's never accounted for, even though that's in a real world scenario. They're just trying to get a rough estimate and predictions based on the force of gravity and all that kind of stuff. So you have to take that for what it is. Anyway, no arrows on this one, again, for the same reason the other one didn't have arrows. Okay, determine a sine equation to represent the writer's path. This one's a little different because now I don't want this as a starting point, because sine graphs start at the midline. So I'm going to go ahead and choose this one as my starting point here. This is at 45 at t. If we're talking about t equals 45 right there, or technically h equals 45, right? That's the whole idea. Hold on. That's the whole idea on this, right? That's 45 in. So I want that to be my reference point for this thing. So let's go with that. That's h. H is 45 there. Now k is my midline value, which is 60. A is my distance from peak, midline to peak or trough. So that's also going to be 60. In this case, it was always going to be 60, but k was actually supposed to be at, 70, I guess? I gotta let it go. And b is the 2 pi divided by period. The period is 180. So 2 pi over 180 is pi over 90. So it looks like this equation is going to be h of t equals, I have a little less room this time. Let's do this down below. H of t equals 60, positive 60, times the sine of pi over 90 times the quantity t minus 45, parenthesis, square bracket, plus 60 on that k. That should be 70. How high will the writer be after 10 minutes? Now, this is measured in seconds right here. So it's not like you put the 10 wherever, a third of the way to the 30 like that. You have to go t equals 600 seconds, right? So 600's right here. So you could get a rough estimate of probably around what's between 90, probably around 90 there is going to be. But we substitute this in for t, and then we determine what that is there. So we can use this h of equation. h of 600 equals, and we have 60 times the sine, just make it a little smaller here, of pi over 90 times, what's 600, I want to take out some work. 600 minus 45 is 555. Surely those reduce, I just don't know how much, plus 60. Let me use my calculator quickly and get a reduced fraction of 555 over 90 without lingering on that. That's not the point of this problem. I do want to see if I can do it without a calculator, though. I mean, for the actual trig portion. How do I convert this to a fraction on this calculator? That's right, fraction. 37 over 6. Okay, so that would be 37 pi over 6 inside there, which means it is a multiple of pi, of pi over 6. That means it's a special angle. So 60 times the sine of 37 pi over 6 plus 60. Okay, what's 37 pi over 6? 12 pi, 2 pi is also 12 pi over 6. So another 12 pi over 6 is 24, and 36 pi over 6. So coterminal with 2 pi is also 36 pi over 6. 37 pi over 6 is another pi over 6 from 2 pi. So it's equivalent. This is coterminal with just pi over 6. I'm not saying 37 pi over 6 is the same number as pi over 6, but the sine of 37 pi over 6 is the same as the sine of pi over 6. And the sine of pi over 6 is 1/2. So h of 600 is 60 times 1/2 plus 60, which is 30 plus 60, which is 90, which is 90 feet. So much like what was probably a good estimate right there, 90 feet seems to be the way. And you know, if you did draw a straight line version, I don't know if this will hit it or not, but if you do draw a straight line version from peak through trough through midline to peak right there, you can see that doesn't hit 90 yet. It doesn't even really hit close to 90 when all things considered. It's under 80. I mean, that's not a good estimate right there. That's, one reason why you don't go jagged edge result on that. All right. When will the rider be 100 feet above ground for the first time? And it's important they say first time for a couple reasons. For one, there's more than one time as the first time. And for another reason, your calculator would actually only give you the first time on its own. You'd have to do some good work to figure out what the answer is beyond that. So 100 feet above ground, again, the way ours is drawn is a little different because it's not what was supposed to be 10 feet. But 100 feet above ground hits 8 times during this ride. When does it hit just the first time? When does it hit right here? And again, the reason the first time is important is because this will have to be some sort of inverse sine answer. We have to go backwards to solve for t instead of for h, and in doing so, we do have to take inverse sine, and it's only going to give you that first one. You're going to have to understand coterminality to try and find out what the answers are for the other ones. It's not hard, it's not impossible at all, but your calculator is going to generate this one for you. So here we go. What you have to do is solve for t, knowing that h of t is now 100. So your height is 100. So we're going to use the same equation, but now we're going to say 100 equals 60 times the sine of pi over 90 times the quantity t minus 45 plus 60. And this just takes some steps here. You just got to work and get t by itself. People get confused in their own work saying it's a lot of work. That doesn't make it hard. Just one step at a time. T is buried in that high castle where you got to cross the bridge, slay the dragon, bust down the open door, take out 2 guards, do whatever, and unlock the shackles and all that stuff. Let's start by subtracting 60 from both sides. We get 40 equals 60 times the sine of pi over 90 times t minus 45. Then we have the 60 to divide because it's multiplying with sine. 40 over 60 is also 4/6 or 2/3. So 2/3 equals the sine of pi over 90 times t minus 45. Sorry, square brackets turned to parentheses. That's okay. To get rid of the sine portion on this side, we actually have to take the inverse sine of both sides. And if you don't mind, I'm also going to put this portion here on the left side of the equation now that we're kind of working this out. So I'll do pi over 90 times t minus 45. So where did sine go on this side? I just took the inverse sine of this side to cancel out sine. That means you have to take the inverse sine of this side to introduce it. Inverse sine of 2/3. And that means I'm going to have to use a calculator on this one, because inverse sine of 2/3 is not a value that I know, because it's not a special angle of any sort. Okay, this pi over 90. Yeah, it looks weird, and you could write it different ways here, but I'm going to multiply both sides by 90 over pi, right, times 90 over pi. To make this as clean as I think it should look here, I'm going to get t minus 45 equals, I like writing 90 times the inverse sine of 2/3, all divided by pi, and then add 45 to both sides. You'll get t equals 90 times the inverse sine of 2/3 over pi plus 45. And make sure that plus 45 is outside of the thing there. So that's an exact answer in seconds. That's a little too exact. Someone's like, holy moly, he's 100 feet in the air. How long has it taken? According to my stopwatch, it's been 90 times the inverse sine of 2/3 over pi plus 45 seconds, sir. Oh my gosh, that's so many seconds. Actually, it's been more than a minute. Like, if someone really knew, holy moly, that's more than a minute. That'd be pretty incredible. Let's take a look and see what the calculator says on this thing, because it's not one that I know off the top of my head. I'm going to expect it's more than a minute. I'm going to hope that all my work was done correctly. Now, you want to make sure, this is my conversion before, you want to make sure that you are in radians for this thing, and my mode is in radians, even for the, especially, well, either way, for the inverse sine portion. So 90 times the inverse sine of 2/3 divided by pi plus 45. All right, 65.9 seconds. So as that other person said that thing out loud, so t is about 66 seconds, 65.9 seconds there. When they're like, oh, it's about this much time. Holy moly, that's 65.9 seconds. That's over a minute. That's how long that one is. So pretty cool stuff that you can do with word problems. I actually tend to like them because you have to know how to get the equation based off the stuff, but you get context to apply for why are we doing this, how can we use it. You get to build a graph based off information, and that information is based off logic of word problem things that you probably somewhat understand. You can actually get a grasp of what that thing means. I like this application a lot, and I hope you do as well. And I hope I get to do more with you guys on these ones as we see fit. All right, guys, so that ought to do it for this one here, for the enrichment material. This is Mr. Robinson. Thank you so much for watching. My game got blacked. Oh, I must have changed the channel by accident. Thank you so much for watching here with this one. And actually, to fill things out, some people have sometimes asked, what's happening here? Some people have sometimes asked why I don't have animation things on these slides anymore. I don't know what's going on. I'm gonna shut this off. It's because I used to have a long cable drawing from a computer that I had over here into the TV to play some slides of backgrounds and animation stuff, and I use that cable in my classroom now for other things. And I don't have my computer up here anymore for that. But anyway, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Take care.